Hello and welcome to yet another Korean College Scholastic Ability Test video. Today we are going to take a look at quite interesting problem from this year's test, which is related to the graph of the function. So let us take a look at the problem itself. For natural numbers n, define fx as absolute value of 3 to the power of x plus 2 minus n when x is negative, and absolute value of log base 2 of x plus 4 minus n when x is non-negative. For real numbers t, let gt be the number of distinct real roots of the equation fx equals t. Find the sum of all possible values of natural numbers n such that the maximum value of gt becomes 4. Now what's really interesting about this problem is that it does not require some fancy calculus skills to solve this problem. This problem actually tests your combined knowledge about the graph of the function, such as graphs of exponential and logarithmic functions, how does the graph change by adding and subtracting numbers, as well as your ability to draw the graphs with these absolute value signs. And that's what makes this problem pretty cool. Alright, so let's draw the graph of this function, but you can already see that it's not easy with all these divided cases and exponential and logarithms and undetermined natural number n and absolute value signs. We need a clever strategy to systematically sketch and analyze this graph. The first thing to notice is that this graph is essentially divided into two regions, when x is negative and when x is non-negative. Whatever crazy thing happens with this n changing, the graph on the left side of the y-axis will always come from this exponential function, and the graph on the right side of the y-axis will always come from this logarithmic function. So our basic strategy would be like this. We will investigate the graph when x is negative and when x is non-negative separately, and then we will combine the result to obtain the full graph. Alright, so first, when x is negative, in this case we have to draw the graph of this function. And in order to do so, we are doing some kind of reverse process and take a look at the easier functions first. For example, we must first draw the graph of this function without absolute value sign. Then we can obtain this graph by simply taking absolute values on this graph. Similarly, the simpler version of this function is this function without subtracting natural number n. And where does this function derived from? Well, it is derived from this function, a simple exponential function y equals 3 to the power of x. So let's take a look at the graph of this function first. It is a simple increasing exponential function passing through the point 0, 1. Also, when x goes to negative infinity, the value of the function approaches 0, which means that the graph approaches indefinitely closer to the x-axis. In other words, this x-axis is the asymptote. Nothing so complicated, right? Alright, now how can we obtain this function? You see, replacing x with x plus 2 means translation, more specifically, translating by negative 2 units along x direction. So if we translate the graph, we obtain this graph. You can easily check that the y-intercept becomes 9 by setting x equals 0, and since we have moved the graph only along x direction, the value of the function still approaches 0 when x goes to negative infinity. That is, this x-axis is still an asymptote. Next, let us subtract n from this graph. This is the translation along y direction. More specifically, this means the translation of negative n units along y direction. Therefore, we obtain this graph. You can see that the y-intercept has become 9 minus n, which can be either positive or negative depending on the value of n. Moreover, now the graph intersects with x-axis as well, so what is the coordinate of x-intercept? Well, by letting this equal 0, we have 3 to the power of x plus 2 equals n, therefore x plus 2 equals log base 3 of n, therefore x equals log base 3 of n minus 2. Therefore, this x-intercept is log base 3 of n minus 2, which also can be positive or negative depending on the value of n. Also, you can see that now the graph approaches different horizontal line, which is y equals minus n. So now we have a new asymptote, y equals minus n. Now finally, this graph. Now we have to take an absolute value sign of red graph, which is simply flipping over the negative part of the graph over x-axis. So we finally obtain this graph. Now the asymptote becomes y equals n, which is always on the positive side because n is natural number. So we have finally obtained the graph. On the negative x side, by the way, the next step is that we should take a closer look at this. This y-intercept and x-intercept can be either positive or negative depending on the value of n. In other words, we have to investigate how the graph changes when we change the value of n. And the first case that we are going to take a look at is when this natural number n is very small, like from 1 to 4 as written in here. Why 1 to 4? Well, we will get to that later. Anyway, here we have our graph, now only defined when x is negative. So this y-intercept is 9 minus n, x-intercept is log base 3 of n minus 2, and this asymptote is y equals n. When n is in this range, y-intercept is located above this asymptote. But things get slightly different when n becomes larger. For example, now we have n from 5 to 8. Then the graph becomes something like this. You see the difference? Well, here, this y-intercept is still positive because it is 9 minus n, and similarly, this x-intercept is still negative, but the y-intercept is now below the asymptote y equals n because 9 minus n now becomes less than n. Now let's see what happens when n becomes exactly 9. You can easily notice that this y-intercept becomes 0 when n equals 9. Moreover, this x-intercept also becomes 0 when n equals 9. So now we have this graph. With both x and y-intercept becoming 0, the graph now passes the origin, and the asymptote is y equals 9. The final case is of course when n becomes greater than 9. As you can see, the y-intercept 9 minus n now becomes negative, and the x-intercept log base 3 of n minus 2 now becomes positive. So if this coordinate is 9 minus n, what would be this coordinate? N minus 9, right? So in this case, y can only have values that are greater than n minus 9 and less than n. Alright, so far we have investigated this graph, which is defined on negative x region, but this is only half of the graph of fx, right? We still have the other half. So now we have to investigate this graph, y equals absolute value of log base 2 of x plus 4 minus n. And we basically do the same reverse process all over once more. So first we think about this graph with no absolute value sign, but before that we think about the graph before subtracting n, but first we think about the most basic one, which is y equals log base 2 of x. This is just a basic logarithmic graph, only defined when x is positive, passing through point 1, 0. And this time, the graph does not approach certain line when x becomes infinitely large. It simply blows to infinity. Actually, this time, this y-axis is the asymptote, which you might already know if you have learned about basic logarithmic functions. Next, we have to translate this graph minus 4 units along x direction to obtain this graph. So we have a graph like this. You can easily find this x-intercept and y-intercept by simply letting y equals 0 and x equals 0 respectively. Also worth mentioning is that now the asymptote has moved to x equals minus 4. The next step is translating minus n units along y direction, then we obtain this graph. Now let's be quick. This y-intercept, letting x equal 0, we know that it is 2 minus n, which can be either positive or negative depending on the value of n. This figure shows the case when it is negative. Also, this x-intercept, well, letting y equal 0, we have log base 2 of x plus 4 equals n, so x plus 4 equals 2 to the power of n, therefore x equals 2 to the power of n minus 4. So it is 2 to the n minus 4, which can be either positive or negative. Now the final step, flipping over the x-axis. Then we have this graph. But of course, you know by now that this specific graph shown here is only the specific case. We have to investigate how the graph changes when the value of n changes. When doing so, we have to take a look at these x-intercepts and y-intercepts. When does this y-intercept become 0? When n equals 2, right? And when does this x-intercept become 0? Also when n equals 2, right? Therefore, we have to divide cases using n equals 2. The first case is when n is less than 2, but since n is a natural number, that case only includes n equals 1. Then we have n equals 2, and then we have n greater than 2. When n equals 1, the x-intercept is negative and the y-intercept is positive, so we have this graph. And when n equals 2, both x and y-intercepts becomes 0, so the graph passes the origin. And when n becomes greater than 2, the x-intercept is positive and the y-intercept is negative, so we have this graph. Since this y-intercept is 2 minus n, this y-intercept is n minus 2. Right, so we have obtained the graph of positive x region as well. If we combine these with previously obtained graphs of negative x, we obtain the full graph of function fx. But let us remind again what we are going to accomplish here. What was the problem again? For real numbers t, let gt be the number of distinct real roots of the equation fx equals t. Find the sum of all possible values of n such that the maximum value of gt becomes 4. So we have to find the number of possible values of x such that fx has certain values. And the best way to do that is by using graphical method. Suppose that this is the graph of y equals fx. Then the number of real roots of equation fx equals t can be found by counting the number of intersection points between graphs of y equals fx and y equals t. In this example, we have 5 intersection points, which means that fx equals t have 5 distinct real roots, so gt equals 5. Also, if you change the values of t and investigate the number of intersection points, you can notice that the maximum number of intersection points that can ever occur in this case is 5. Therefore, in this example, maximum value of gt equals 5. Now in the main problem, we want the maximum value of gt to be 4. And let's get back to the graphs that we've obtained so far. So these are the graphs. I have already explained every single case shown here. Now, in what cases can we have the maximum number of 4 intersection points with some horizontal line y equals t? Well, they are these cases, right? Because we have to have exactly 2 intersection points when x is negative, and also exactly 2 intersection points when x is positive. That is the only way we can have 4 intersection points in total. So if we take a common range for n between upper ranges and lower range, we obtain n greater than or equal to 3 and less than or equal to 8. So with this common range obtained, we can find the answer with no problem. But before we do that, let us actually plot all cases that the maximum value of gt becomes 4, which are these. Here I have divided the cases into n equals 3 and 4, n equals 5, and n is from 6 to 8, because these orders of y-intercepts change along with changing values of n, but that's not a big deal in solving the problem. So the problem asks us to find the sum of all possible values of n, then make maximum of gt equals 4, so we have to add 3 plus 4 plus 5 plus 6 plus 7 plus 8, and this is 11, and this is also 11, and this is also 11, so we have 11 times 3, which is 33. And this is our answer. Thank you all for watching. If you liked this video, please hit that like and subscribe buttons, and also check my other videos, and I will see you in another video.